So calculate the kinetic energy of the ejected electron in the picture above. So this picture, and what this is really referring to is not this one, because we know this one didn't result in photoelectron, but it's referring to this picture right here where we use a 200 nanometer photon, and we know that potassium metal has a work function of 419 kilojoules per mole. Well, as I said, the first thing that I need to do is convert that to joules per single thing. Okay? So I know that 1 kilojoule is 1,000 joules, and I know that 1 mole is 6.022 times 10 to the 23, and I'm just going to leave it like that. I don't have to technically put in atoms or molecules or things, because it's implied that that's just going to be a singular thing that we're talking about, okay? So 419 times 1,000 equals, and then now divided by 6.022 e to the 23 equals, and that looks right, okay? So 1, 2, 3 sig figs, because I had 419, so we'll say 6.96 times 10 to the minus 19 joules equals phi. So I remember that my equation is kinetic energy of the electron equals h nu minus phi. So now I have to calculate this quantity h nu, but I don't have the frequency in this picture. I have the wavelength. So I recognize that h nu also equals hc over lambda. So in this equation, I can also say that hc minus lambda minus phi also equals kinetic energy. Either one of those is okay, depending on what, if I have the frequency or if I have the wavelength. In this case, I have the wavelength, okay? So let's do that calculation. So we know h is 6.626 times 10 minus 34 joule times seconds. We know C is 2.998 times 10 to the 8 meters per second. And here this wavelength, 200 nanometers, I'll put this down here in the notes, or in the side. So I know 1 nanometer is 1 times 10 to the minus 9 meters. So automatically I know that's 2.000 times 10 to the minus 7 meters. Okay, be quick with those unit conversions, all right? So now that's divided by 2.000 times 10 to the minus 7 meters, which is the same as my 200 nanometers, okay? And so when I do all of this calculation, I get, let's see, 6.6626 E. So on my calculator, I have to say 34 and then minus. Maybe that's what you have to do on your calculator as well. So times 2.998 E8 equals, and then divided by 2E7 minus equals, okay, good, that looks right. 9, and then now I had 4 sig figs here because of 200.0. So that's 9.932 times 10 to the minus 19 joules, okay? And now finally, I can say the kinetic energy of the electron is going to be this quantity minus that quantity, okay? 9.932 times 10 minus 19 joules minus 6.96 times 10 minus 19 joules. Okay, and so I'll leave this in the calculator here, and I'm just going to say minus 6.96 E19 minus, and yep, I get, and then 3 sig figs now because of my work function. So that's going to be 2.97 times 10 to the minus 19 joules would be the kinetic energy of that ejected electron. And it's a tiny number because it's one single electron we're talking about, right? And so just like we did in that previous example, you know, going back here, I'll show you, where did it go? Maybe I passed it already. this example, right? Where we can take our energy of one photon and we can multiply it by a mole, and that gives me the energy of a mole of photons. So realistically, you're not going to be shining one singular photon on one singular potassium atom and knock out one single electron. However, these calculations are easiest done under that assumption that it's one single thing. But now we recognize if, let's suppose I had a mole of potassium, or had 5.62 grams or whatever, I can use this number just like my other dimensional analysis numbers and scale that number up if I had more than just one single electron being ejected, okay? So now, calculate the minimum wavelength of light needed to ionize potassium. So it says we're going to do this in the discussion worksheet, and we will. I'll do another example. I'll give you a different example than this one. But now if we think about it here, okay, the minimum wavelength of light needed to photoionize, if we think about this, is going to be, so I'm going to write this as hc over lambda minus phi. The minimum, the bare minimum energy will be when the kinetic energy is 0, because now anything that's slightly more energetic than this number, so the energy that satisfies this equation, now that this all equals 0, that will represent the bare minimum. Okay, hopefully that makes sense. And so now what I get from that, what I can see if I wanted to rearrange this, I could say now, doing the algebra here, phi equals hc over lambda. And I'm going to keep doing the algebra because they asked me for the wavelength, the minimum wavelength, right? And so rearranging now, that's going to be lambda equals hc over phi. Okay, so it's as simple as that. So now I can say that minimum wavelength I need is going to be 6.626 times 10 minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. And then now I have to use my singular value of phi, right? Which was the 6.96 times 10 to the minus 19 joules. Okay, so let's see when we do all of that. So 6.626 E minus 34 times 2.998 E8. Okay, and then now divided by 6.96 E19 minus equals, okay, cool. And that gives me so we'll just say 3 sig figs, 2.85 times 10 to the minus 7, and let's check out the units. So seconds and seconds cancels, joules and joules cancels, and now that's units of meters. So it didn't say to what unit to convert it to, but when in doubt, converting to nanometers is always a good thing, so we can see what region of the spectrum that we're in. So I know 1 meter is 1 times 10 to the positive 9 nanometers. And now this is going to allow me to just do exponent math, right? So minus 7 and positive 9 gives me positive 2. So that's 2.85 times 10 to the positive 2 nanometers. That's the same as 285 nanometers. And that makes good sense because look, when we used a 200 nanometer photon, which remember, 200 nanometers is more energetic than 285. I know the number is smaller, but we have to remember because it's a small wavelength, it's a big energy. Okay, so this 285 is just slightly bigger in wavelength, which means it's just slightly less than energy than 200, and that makes good sense that this 285 nanometer represents a minimum. So if I shined 286 nanometer light on potassium metal, it would not photoionize it. If I shined 285, it would still not ionize it because the kinetic energy is 0. However, if I used 2 84.9, right? Then I would get photoionization. I would get an ejected electron. Okay, so why is this important to know? Well, as it turns out, this photoelectric effect is widely exploited in modern electronics. Okay? So here's an example of a photomultiplier tube, and this is pretty old school photomultiplier tubes, but all the same, we wouldn't have the technology of today if we hadn't had these photomultiplier tubes. These are largely used in older electronics. You might just hear these referred to as a phototube or even just a tube. Like I still love my guitar amp that's a tube amp. Maybe you guitar heads out there know about tube amps. Those are photomultiplier tubes, okay? And so the idea of these things is you can induce a current through light. So here is the tube, the phototube itself. It's an actual tube, right? And inside of it is a vacuum. Okay, so it's evacuated. And here what you have is this positive electrode, so that's the electron collector. And so what ends up happening when light of a very specific frequency or energy, right, it has to be slightly above the minimum energy of whatever the metal is, right? So now when light hits that surface, an electron gets ejected into this collector electrode, and it completes the circuit. Okay, so now you've got electrons that flow and that can flow into this device and out the other device, which is pretty cool. So these are widely used as light detectors. So that's really what this is. This example is showing you this as detecting light because you can see it's got a voltage source already. And so I've got an example of one of these things. It's the remote control to my stereo, right? It uses infrared light, and when I point it at the stereo, it completes a circuit from the signal via this photoelectric effect, and that's why I can use that thing. Okay. Some of them also use radio waves, but more often than not, your remote controls use infrared. Okay. And also, based on the same principle, if we take the battery source away, okay, and we talk about a solar panel, right? Then largely, it's not quite the same as the photoelectric effect, but it's a very similar idea where light is being shined. And now an electron is not ejected into vacuum, but rather an electron gets ejected into some wire. So a wire collects those electrons and can be used for power. So that's pretty cool stuff. Okay. So